Okay, so we now know that our Lagrangian density must be quadratic in phi and that it must also be Lorentz invariant. So let's write down what possible terms we can have. So here are the possible terms. So the first, most obvious one is just phi squared. So that's a definite possibility. Second term that is also very natural is to take the mu phi. So there the derivatives are properly contracted. Now, you might say to me, what about taking something like this? What about taking d mu phi times by phi? Isn't this quadratic in phi and also Lorentz invariant? Well, yes, it is. But let me just make two comments. So first of all, as we discussed, our Lagrangian density should be a function of phi and d mu phi. Now, this depends on a second derivative of phi. So for that reason, we could disqualify this term. But there's another reason why we wouldn't like to consider this term, and that is that I can rewrite it as follows. I can rewrite it as d mu phi, phi. Oh, I don't know what happened there, so let me just correct that. D mu phi. And then when the second derivative acts, when that derivative acts in the first term, by the product rule produce two terms. The first term it produces is when you act on the first phi, that'll cancel against the term that I've added here with a minus, and then it can act on the second term, which is equal to the original term. But what you can see is this term over here is a total derivative, and we can drop total derivatives. So in fact, up to a total derivative, this term that we could write is the same as that term over there. So we don't consider this term, this one that I've just ringed, we don't consider that as a possible term inside the Lagrangian. In fact, there are no other terms that we could have considered that are quadratic in the fields, depend on only a first derivative and are Lorentz invariant. That's it. So the Lagrangian must be a sum of these two terms. Okay, so let's now choose our Lagrangian density. So the Lagrangian density that I'm going to choose, I'm going to say L is equal to, so I'll start off, there's a 1/2 here. That is totally my choice. I could undo it by scaling phi in some way. So setting the strength of the field strength of phi is the same as choosing that coefficient. And afterwards, we're going to see that this is a particularly nice choice of coefficient in quantum field theory. But, you know, things are still completely general. I could have chosen this coefficient whatever I like. It simply defines the strength of the phi field. For the second term, I'm now going to say minus m squared over 2 phi squared. And I've chosen that second coefficient of minus m squared over 2 with the benefit of hindsight. I want this to agree with the field equation that we had before, so I've chosen this term to be something very specific. Good. What I'd now like to do is use this equation to work out what are the Euler-Lagrange equations of motion. So the first term, I think, is pretty easy to calculate, dl d phi. Well, remember, we treat phi and d mu phi as two completely independent variables. So when we come to differentiate with respect to phi, we don't hit the first term in the Lagrangian. We only hit the second term. So we'll get minus m squared phi. Okay, that's the first term that we get. Now let's work out what is dl d mu phi. Okay, I'm going to do this slowly because maybe this is the first time that you're seeing something like this, but this is the kind of thing that you should make sure that you understand well and practice taking these derivatives. Make sure you can do them. So I want to take d by d mu phi And the only term that I'm going to hit now is the first term in the Lagrangian, because I treat phi and d mu phi as independent variables. So I will have 1/2, and I'm going to rewrite that term slightly. I'm going to write it as d alpha phi, the Minkowski metric, which raises and lowers indices, and then a d beta phi. And you see, the reason why I've done that is I'm differentiating with respect to lower index mu. So I've written the Lagrangian completely in terms of lower index fields. That's why I've actually put the metric in there. The metric would just have lifted the beta index and made it an alpha. So this is completely equivalent to 1/2 d alpha phi, d alpha phi. Now you might say, hang on, this is no good. You've got d alpha phi, but in the Lagrangian, you've got d mu phi. Well, remember, this index is contracted, so it's a dummy index, so I can label it to be anything that I like. I've called the dummy index alpha because I'm using the index mu as a free index when I calculate this derivative. So I want to relabel the dummy index. Good. Okay, so now let's calculate this derivative. So when I act on the first term, well, I'll get 1/2, and d mu alpha onto d alpha phi will give me 1 if alpha is equal to mu, and it will give me 0 otherwise. So I'll get delta mu alpha eta alpha beta d beta phi plus, and now I can hit the second index. So I'll get 1/2 d alpha phi eta alpha beta, and then exactly the same argument. I get 1 if mu is equal to beta. So if the mu that I'm differentiating with respect to equals the beta, the thing that I'm differentiating, I'll get 1, and if not, I'll get 0. So I'll get mu beta. That's just the Kronecker delta. And if I now work out what is this, well, I can do the sum over alpha. So I'll just get 1/2 eta mu beta d beta phi plus 1/2 d alpha phi eta alpha mu. So in the first term, I did the sum over alpha. In the second term, I did the sum over beta. And now I can just use that metric to raise the beta and make it a mu. So I'll get 1/2 d mu phi plus, and in the second term, I've got 1/2, and I can use the metric to raise the alpha index and give me a mu, d mu phi. If I add those two, I just get d mu phi. Now, I want you to notice something, and this is a very general rule. It's an absolutely correct thing. When we took this derivative, we had a lower mu index, but this is what we were differentiating with respect to. You know, it was in the denominator. And by the time we finished the computation, this is now an upper index. So whenever you differentiate with respect to a lower index, the result is an upper index. That's a useful rule to remember. There's one more thing that I want to point out. We verified before that eta alpha beta was Lorentz invariant. Okay, we checked this with a specific boost. You know how to check this. I want you to check something else. So I claim delta alpha beta, one index up, one index down, is also Lorentz invariant. Okay, so that's a very nice thing for you to check. So the Minkowski metric and the Kronecker delta are both Lorentz invariant. Good. Okay, so now what is the Euler-Lagrange equation? Well, dl d phi should be equal to d mu dl d mu phi. Dl d phi was minus m squared phi equal to, now we'll have d mu, and dl d mu phi was d mu up phi. And we see nicely the mu indices contract with one index down and one index up, so that the equation of motion that we get from the Euler-Lagrange equations is this equation sitting over here, which you will recognize as the Klein-Gordon equation. And this was exactly the equation that was obeyed by our scalar field. So to summarize, here are the key points. The Lagrangian for a free scalar field takes this form. And you can see now I picked the second coefficient of minus m squared over 2 so that I'd get the correct Klein-Gordon equation. The equation of motion is that boxed equation, and the Euler-Lagrange equation is the equation that I am boxing in green. So those were the important parts from this lecture. Good. Okay, that completes our discussion of Lagrangian field theory. The only thing left to do now is to discuss the exercises.